Hey guys, Mr. Smith here, and in this video we are going to update our definition of gravitational potential energy to make it work for very large distances too. So let's get started. So in our last lesson we talked about gravitational field strength, and because G is gm over r squared, as you get farther and farther away from an object, so as r increases, G is going to decrease. And if that change is very big and the change in G is very big, then our old expression for gravitational potential energy is not going to be very good anymore because G is not constant, it's changing. Now, in theory, this old formula always had a bit of error in it if you were actually changing your distance above the Earth's surface, because G would change. But because the difference in G was so slight, we didn't see any difference. But in the kind of problems we're going to be doing in this lesson and next lesson, specifically looking at satellites and trying to launch things so they escape the Earth's gravity, our change in distance is going to be very big. And so this old formula is not going to cut it. So we need a better formula. We need something that works. So we're going to do that right now. We're going to consider two large masses. So we're going to call them M1 and M2 in a second, a large distance apart. What this graph shows you, this is a force distance curve, or FR curve. And the curve you see on there, or the function you see, is G M1 M2 over r squared. It's actually the gravitational force between two objects. Now G, and if we consider our masses to be constant, then the shape of this graph has the same shape as the function y equals 1 over x squared. And if you've only taken up to grade 11 math, maybe you only saw the function 1 over x, but I can tell you the shape of that graph is very similar. It looks like this. And so you can see the upper portion of this graph is what we see here. So you can see it decreases really rapidly, and as r gets really big, this gravitational force gets to 0. And the key idea is we know that, for just like a constant force, we've been using, work equals force times distance, assuming they're in the same direction. We're doing something similar here. And to get the work done in this case, separating two masses, we find the area underneath this curve. So that's how you can find work in general, is by finding the area under an force displacement curve. We're going to do it here. And now the issue is that's a very funky looking shape. It's not something we, on our formula sheets from like EQAO in grade 9, right? How do we find the area under this curve? So we're going to talk about it in a way that works for everybody. And then I will show you also how you can use calculus to deal with that. But so here's our starting point. So the change in gravitational potential energy, that's equal to the work done to bring them apart. So we need to add energy to that system. These two massive objects, they want to attract. So we have to actually do work to pull them apart. And that work is given by the area under our FR curve. So for those people who have taken calculus, I will show you how to do that in a minute or two. But because most of us haven't taken calculus, I'm just going to give you actually an equation for the area underneath a 1 over r squared function like that. And the area under the curve is given by this. So this, you'll just have to take my word for it. Again, if everybody here had taken calculus, then we could all just use that. But just take my word for it. The area under this curve is this horizontal distance between kind of like the base of this like rectangle, R2 minus R1, times the root of the product of this y value, this force value here, and this force value down here. And that's our starting point, because we actually we know an expression for the force, right? So we have the root of, well, what's F1? Well, it's G M1 M2 over R1 squared. F2 is G M1 M2 over R2 squared. And then outside that root, we have R2 minus R1. And at this point, a lot of cool things happen. So you're going to have G times G, but then you're rooting that. And the same with M1. You'll have M1 squared square root, M2 squared square root. So we're going to have G M1 M2. And then you'll have R1 squared, which is, and then rooting that gives you R1. And R2 squared, you're rooting that gives you R2. And then you're still left with R2 minus R1. And I think I have room for one more step on this. I do. I'm going to use the distributive law. So when I use the distributive law, think what happens. When I multiply this expression by R2, well, then the R2 on the bottom is going to divide out. And I've got G M1 M2 over R1. And then when I multiply by the second guy, it's the R1 on the bottom that gets canceled. G M1 M2 over R2. Now, we're looking for the change in gravitational potential energy. So that's always the final minus the initial, right? But look what we have here. We have an expression for the initial minus the final. So we want to do a little bit of manipulation here. So we get an expression that's final minus initial. So we're just going to play around with signs a little bit here. So you guys on your sheet, this will just be your next line. For me, I've got to go to a new slide. But so I'm just going to do a bit of reordering. So I'm going to put the second term first, negative G M1 M2 over R2. My first term was plus GM GM1 M2 over R1. But I can write that as subtracting negative G M1 M2 over R1. And so that's just the previous line. I'm just moving things around, playing with the signs a little bit. And if we let EG be equal to negative GM1 M2 over R, then the expression we have here is actually a final gravitational potential energy minus an initial gravitational potential energy. And so guys, what we've done is we've got our expression for gravitational potential energy between two objects where the distance is large. It's this. EG equals negative G M1 M2 over R. So I have a couple just a little notes to add. This is, I think, yeah, I have in my spot for other notes, I'm going to have some spots for things, but for now, I just want to mention a couple just on the slide. I'm just going to write them in. This expression is equivalent to the work done moving mass 1 and mass 2 together from far away, r equals infinity. So we just have to unpack that a little bit. When we were doing EG equals mg delta y, we were using h equals 0 or y equals 0 to be like maybe the Earth's surface. And we were raising it above the Earth's surface and we were adding energy. We had to do work to lift something up. This new way of doing gravitational potential energy requires a bit of a change in thinking. So in this case, when is the force on the object 0? It's when, or between the two things 0, it's when r, the distance between them, gets really, really, really big, i.e. r equals infinity. And so we're now using our reference point, instead of being h equal to 0 and lifting it above a surface, we're thinking of two objects and bringing them together from infinitely far away. So R equals infinity is like our new reference point. That's going to take a little bit of digesting for some or many of you guys. This value is negative. So you might be thinking, well, how can it be the work done moving these two together if it's negative? Well, work can be negative. We can also think of this expression as remember, work is a transfer of energy, and we can remove energy from a system. Energy can be lost. You can also think of it as the energy lost, as M1 and M2 move together from R equals infinity. Because if you think about it, if you have two objects that are a certain distance apart, do you have to work to force them together, or do they naturally just want to come together? They naturally just want to come together. And so when two things come together gravitationally, energy is being removed. But when two things are being pulled apart and their distance increases, that's when you have to work at it and do work. So if we have that frame of mind that our reference point, where EG is 0, is infinitely far away, this definition makes sense. And again, as we bring objects together from far away, energy is removed from the system. We have this negative potential energy. So again, that's going to take some getting used to for some of you. Now, if you would like to skip over this slide, that's totally fine. This will only kind of make sense for people who have taken calculus. But the work done to bring these two together, this change of potential energy, it's the area under the curve. And so if you've taken calculus, maybe you've seen that the area under a curve you can find using integration. It's the integral from R1 to R2 of this curve. And this curve is G M1 M2 over R squared. And we're integrating that over R. So we'll add dr there. Now, G, M1, and M2, they're all constants. So they can actually come outside of this integral. And so we're really just integrating the function 1 over R squared. So for people who have taken calculus, finding an integral is like the opposite of finding a derivative. So what is what function, when you take the derivative, gives you 1 over R squared? Well, calculus people would know that that's negative 1 over R. And our two endpoints for that are R1 and R2. So what this notation means is we plug in R2 and we subtract plugging in R1. And if we don't have to clean this up. We just get the exact same expression we got before. And then we have subtract negative G M1 M2 over R1. And we come to the same conclusion as before, that the gravitational potential energy is G M1 M2 over R. So yeah, if you want to just pretend that those 2 minutes just never happened because you haven't taken calculus, or even if you have, that's totally okay. That's just purely optional. I didn't have a space for you to do that on your sheet, so you don't need to copy that down. Other notes. So this EG, and here I've just kind of rewritten it. Instead of M1, M2, often we'll be considering the gravitational potential energy of, say, like a satellite above a planet. So we'll often have one big mass and one little mass. So this is the same thing. Instead of M1 and M2, it's big M, little m. It's always negative. And again, it's always negative because energy is lost as two objects come together from far away. Now, EG is always negative, but a change in gravitational potential energy can be positive. So if we're increasing the distance between two things, just like lifting something off the Earth, we're storing energy, and that change is positive. But if you bring two things closer together, you are removing energy from that system. So this graph just kind of tries to give you one extra resource to help digest this. Here's the curve. Here's what the curve negative GMM over R looks like. It kind of looks like your 1 over x function from grade 11 university math, but kind of reflected in the x-axis, flipped over. And you can see that as r gets really, really big, if you divide by a really big number, you get a really small number. So EG equals 0. So as the distance between two objects gets bigger and bigger and bigger, our EG goes to 0. Again, this idea is going to take some getting used to for many of you. And that's okay. Everything can't be a slam dunk. I know it certainly for me, it took me a while. Probably in high school, I probably just I did well, but I probably just kind of okay, that's the formula, and it's fine. And I just used the formula. I didn't really have to have a deep understanding. But I can honestly say it was only when I started teaching physics that I really developed a deeper understanding. So it's okay for you if it doesn't come together immediately. It might take a little bit of wrapping your mind around. That's totally fine and acceptable. And it's nobody's fault. You're not, nothing's wrong with you if something doesn't sink in right away, and nothing's wrong with me. I didn't teach it poorly or anything. Some concepts are just kind of tricky, and it just takes a bit of time to sink in. Of course, there's probably a lot better teachers who can probably, working at universities, that can probably give you a good lecture on this, but we're all doing the best we can. All right, let's play around with that now. So let's find the change in gravitational potential energy of an astronaut lifted from the Earth's surface to 520 kilometers above the Earth's surface. So we're going to use the old formula and the new, and then see how they compare. So it should be pretty interesting. And it's just going to give us a bit of practice. So I'm actually going to do the old first, and I'm just going to do it up here because it's not going to take much space. So delta EG equals mgh2 minus mgh1, or if you prefer, mg delta h. Just, if you factor out mg, you get h2 minus h1. And so little m is the mass of the astronaut. So it's 55. And, we're doing it the old way. So we're assuming that g is constant. So 9.8. And our change in height was 520 kilometers. So 520,000 meters. So let's get that change in energy the old way. So that is how accurate do you want to be. So that's about 2.8 times 10. How many zeros is that? I think it's 8. I got 8 before. So that change in energy about 2.8 times 10 to the 8 joules. So let's see how the new formula does. So I might show kind of a lot of steps actually, just to make sure people are comfortable using the formula. So we're going to calculate some gravitational potential energies using our new formula, doing EG2 minus EG1. So this will be G big M little m over R2 negative, subtract minus G big M little m over R1. So I want to do this the long way. I want to calculate each of these individually and show you that even though they're both negative, when we find the change in potential energy, we're still going to get a positive result. So just in case you weren't quite convinced. So I know I could do some factoring here to probably save myself a bit of writing, but I do actually want to find each one individually. So I'm going to put some square brackets here. Let's get this first one done. So negative 6.67 times 10 to the negative 11. Mass of the Earth, always forgetting the mass of the Earth. 5.98 times 10 to the 24. Little m, our second mass of the astronaut, 55. And R2, so the new radius, our new R, is 520 kilometers above the Earth's surface. So we're taking the Earth's radius, which is 6.38 times 10 to the 6. And we're adding on 520,000. in terms of scientific notation, if you prefer that, 5.2 times 10 to the 5. So that in itself is a pretty chunky calculation. And let's also find the gravitational potential energy at the surface. So minus 6.67 times 10 to the negative 11, same mass. So again, I know this mathematically could have been done quicker with some factoring, but I have a reason why. And R1 is just at the Earth's surface, so 6.38 times 10 to the 6. Okay, let's find those two individually. So I have actually done this before, but you guys are slogging it out. And so I'll slog it out with you and just do the calculation as well. 6.38 x6 plus 5.2 x5. That's the theme of COVID, right? We're all in this together. Okay, so that number definitely seems off. So check that again. Negative times negative 5.98 x24 times 55 divided by 6.38 x6 plus 520,000. Okay, that's better. So I got about negative 3.2. What have I done? That number is way too big as well. Did I use the right? Let's try this one more time. Maybe I should have just copied down my file. Maybe I should just copy down my answer from before. Let's see if the third time's a charm here, guys. Yeah, this will work. I actually felt like I've had a pretty smooth run of videos without making too many mistakes. All right, there we go. Minus 3.2 times 10 to the 8 joules. So it is a negative value again. We're subtracting, and now let's do this calculation. Let's see if I can do it the first try. Times 55 divided by 6.38 x6 equals, all right, about negative 3.4 times 10 to the, actually that's 10 to the 9. Yes, that was 10 to the 9. And that's 10 to the 9. And if you subtract those two values, lo and behold, let's do negative 3.2 x9 plus 3.4 x9. We get about 2 times 10 to the 8. And so you'll notice since we're subtracting a bigger negative number, it works out to be positive. Just like, if I was to do negative 2 subtract negative 3, that's like negative 2 plus 3, which gives me a positive, right? So it's the same thing works out here. And we get about 2 times 10 to the 8. So if we compare and we see how the old formula does, so if we take the, to find the percent error, so what we're doing is we're taking the new correct value, so 2 times 10 to the 8, and we're going to find the magnitude of the difference between that and the old value, and then divide by the new value. We're going to see what percent this old one is off by. So 2 times 10 to the 8, actually I think we can just divide it by 10. So 2 minus 2.8 divided by 2. And so in terms of, with the absolute values, think in terms of a positive sense, you get 2.8, 2.6, so you get about 40%. Now, if we had kept a bit more accuracy, maybe that would be, give or take a little bit. But we can see that, yeah, the old guy, like that's a pretty significant difference. And I would argue even if we kept more accuracy and maybe it dipped down to even like 10%. I think actually keeping another decimal place would have affected it a lot. It's still quite a big difference. And so we can see how we need this new formula. So the purpose of this example, I wanted you guys to just get practice calculating a gravitational potential energy, become okay with the fact that it's negative, because you're convinced if you're separating two objects, you are going to get a positive change in gravitational potential energy. We're going to do one more example, and this actually isn't comparing formulas. This is just actually applying conservation of energy. So we're considering an object on the Earth's surface, and we're launching it up in the air so that, kind of like a projectile, it reaches some maximum height and then it comes back down. And we want that maximum height to be twice the radius of Earth. So that's the idea here. Now, when we were doing problems, maybe in grade 11 or while reviewing, we might have chosen that, for our perspective, like a level Earth surface to be h equals 0. We don't do that anymore. The 0 case is infinitely far away. So when we set this one up, E before equals E after. So I'll say EG1 plus EK1, no springs in this question, equals EG2 plus EK2. So initially, that should be EK1. We're giving the object some kinetic energy, but it has some gravitational potential energy as well. And when it's reached the top of its arc before coming back, we've got some gravitational potential energy. But the one thing that can be 0 in this problem is that final kinetic energy. At that max height before coming back down to Earth, it'll be 0. So we need conservation of energy for this question instead of using projectiles, because when we did our projectile motion stuff, we use constant vertical acceleration due to gravity. But now we know for large distances, G is not constant. In fact, it changes quite a bit. So we need conservation of energy to solve this problem. So let's plug in what we know. So EG1, at the Earth's surface, the gravitational potential energy is G, big M, little m. So I'll use big M for Earth, little m for my object. And my r at the Earth's surface would just be the radius of Earth. And I have to give it some speed. So 1/2 little m, so it's the speed of the object. And I'll just call it v, because that's the only v in the problem, since we're v2 equals 0 over here. And then finally, we get negative gmm. And we're now, if we think what r is for the second point, remember r is center to center separation. If we're 2 Earth radii above the Earth's surface, that means we're 2 plus 1, 3 Earth radii away from its center. So our r for afterwards is 3 RE. And I'll do maybe a bit of an extra step here before rearranging everything. So one, notice the little m's all divide out. So we're used to that in a lot of conservation of energy problems that don't involve springs. And this negative gm over RE is actually a like term with negative gm over 3 RE. So I'm just going to show an intermediate step here. I'm going to bring that term over. So gm over RE minus, I'm going to write it maybe a different way, minus 1/3 gm over RE. So now we basically have 1 minus 1/3, and we get 2/3 gm over RE. And now we can solve. For v. So we're going to. Oh, I didn't divide out my m, so that's just 1/2 v squared. My apologies. So we're going to multiply up to 2. So we'll get a 4 gm over 3 RE for this problem, and we'll be square rooting that. And so that'll give us our desired height. And we know all those things, so let's finish the problem off. And mass of Earth, do I have it memorized yet? 5.98 times 10 to the 24. 3 times 6.38 times 10 to the 6. I think those are the values. Yes, we've reached that point in the course where I've used them enough that I have them memorized. Maybe you do too. Times 5.98, x 24, divided by 3, divided by 6.38, x 6. So, I mean, we're finding a speed here. So that speed is probably going to be pretty big. Yeah. So 9,130 meters per second. 9 kilometers per second. So keep in mind, that's not saying, oh man, well, how would we ever get to the moon then? Because like, how can you ever like fire something at a speed of 9 kilometers per second? But that's like if you're treating it as a projectile. So in reality, you know, a rocket ship is burning fuel to constantly just like accelerate it upwards. And it doesn't have to reach a speed like that to get that high. It can be done more gradually over time. But this is the case where you're not providing a constant source of fuel or force. This is just like you have a giant slingshot. How fast does your slingshot have to be or you know, you'd have to fire that something in a slingshot at about 9 kilometers per second for it to get that high. So pretty interesting. All right, so we've now updated our definition of gravitational potential energy. We've seen that this new interpretation, we get a negative value, but when we do changes in gravitational potential energy, we can still get positives if we're moving things farther away. And we also did a conservation of energy question, getting us ready for our next lesson about things like escape speed. So if I actually wanted to fire something from the Earth's surface so it would never come back, how fast would I have to fire it at? And if I have not maybe something on the surface, but say I have some spaceship that I want to send to Mars, and right now I've put it in orbit around the Earth. How much more energy does it need in order to escape the Earth's gravitational field? So I kind of call this rocket science. Really looking forward to doing that lesson with you guys. We'll also be able to talk about black holes next lesson as well. Lots of cool stuff. But for now, I'm going to sign off. Hope you guys are staying well. Have a great day, and we'll see you soon.